torsion occurs on certain components which are subjected to torque or twisting moment. So this is seen in certain applications. For example, the rotating shafts, as in the case of engines, motors and turbines. Even though the component, it is not rotating, it is static, as in the case of bolts and screws. These are also subjected to torsion. So torsion induces shear stress on the component. The material fails by torsion due to shear alone or shear stress accompanied by bending and stretching. This torsion test do not require any specifications for the specimen, unlike in the case of tension test, which uses a standard tensile specimen according to ASTM standards. Torsion test can be conducted on very large parts, shafts, axles, etc. And this is not as widely used as that of tension test. This is used in certain applications where the component is subjected to torsion, or for certain applications where the component is subjected to very large amounts of plastic strains. To know the behavior of a material under large plastic strains, one can use this torsion test. So from the torsion test, the twisting moment and the angle of twist are measured, and from which shear stress versus shear strain curve can be constructed. And one can determine the shear stresses and shear strain and modulus of shear within the elastic region or within the elastic strains. So for the case of torsion test, circular geometry specimens are used because this is the simplest geometry to measure the stress. Stress varies 0 at the center of the specimen to the maximum at the surface. In order to determine or derive the torsion equation, we consider a shaft of length L. A shaft of length L which is having a circular cross section of radius R. In the case of torsion test, the specimen is held between two heads. One is stationary, one end is stationary, and the other end it is being gripped, that is the twisting head. It is being twisted. So as the specimen is being twisted, deformation is measured by means of proptometer. Angular displacement of a point on the specimen is measured relative to the same point, relative to the same element at the opposite end. So in considering a shaft of length L and radius R, we derive the equation for the torque. So a line drawn to one end of the face, a radial line drawn when this is subjected to, when one end is subjected to a torque or twisting moment, this radial line, it displaces to an angle theta. So this length of arc or length of this displacement, it is given by r theta. So now imagine a line drawn parallel to the axis where it is subjected to a twisting moment. This line displaces to an angle gamma. So this length of arc is equal to L gamma. Assuming that both these lengths are equal, L gamma is equal to r theta. Assumption is both these lengths of arcs are equal. We have gamma is equal to r theta by L. So this is one equation. So for strains within the elastic region or for elastic strains, shear stress, which is represented by tau, that is equal to shear modulus into shear strain. This is equation 2. From this equation, we substitute for gamma. So that is equal to tau by G is equal to r theta by L. So this is equation 3. Shear stress varies along the radius of this shaft. It is 0 at the center and varies linearly along the radius and is maximum on the surface. So assuming that this equation holds for any radius, we have tau by g is equal to small r into theta by L. So when torque is applied onto the component, onto this shaft, internal forces tries to resist this twisting moment. So we consider a small elemental ring at radius small r, a small elemental ring dr at radius small r. This radius small r, this is a small elemental ring dr over which shear stress is acting. The area of this elemental ring dr is dA, that is 2 pi r dr. The force on this elemental ring is equal to shear stress into area dA. From this we have tau into 2 pi r dr. So when twisting moment or torque is applied, the torque that is subjected to this elemental ring, torque is dt. Torque is equal to force into distance. So that is, force is given by this equation, tau into 2 pi r dr into small r. So from this we have torque is equal to tau 2 pi r square into dr. So torque on the elemental ring is equal to tau shear stress into 2 pi r square dr. From this equation, tau is equal to g r theta by L. We have d theta is equal to g r theta by L. This was written in place of tau 2 pi r square dr. So this further simplifies into g theta by L into 2 pi r cube dr. So dt is equal to the torque on the elemental ring is equal to g theta by L into 2 pi r cube dr. So when this is applied for overall cross section, we have T is equal to g theta by L into integral 0 to capital R 2 pi r cube dr. So this equation, it is applied for the whole cross section. So integrating between the limits from 0 to capital R, we have torque T is equal to g theta by L integral 0 to R 2 pi r cube r, where this is called the polar moment of inertia indicated by the symbol capital J. It indicates the ability of a material to resist the twisting moment or torque. Higher is the polar moment of inertia, higher is the resistance to torque or twisting moment. So this equation can be further simplified into, this is the equation 4, which is further simplified into T is equal to g theta by L. This integral is J, that is polar moment of inertia. So from this we can write T by J is equal to g theta by L. So this is the equation for torque, where J can be obtained by this integration 0 to R 2 pi r cube dr, which is the polar moment of inertia. On integrating between these limits, we have 2 pi r to the power of 4 by 4 between the limits 0 to r, which further simplifies into pi r to the power of 4 by 2 between the limits 0 to r. This equals to pi capital R to the power of 4 by 2. So this can be written in terms of d, pi d power 4 by 32. which is the polar moment of inertia, that is J. So the equation for the torque is T by J, torque by the polar moment of inertia, is equal to the shear modulus into theta, that is the angle of twist, by L, that is the length of the shaft. So this is the equation derivation for the torque. The importance of this torsion test is it can be conducted on to a very high strain rates, at constant strain rates, as well as very large plastic strains can be achieved in the case of torsion test. This does not suffer from the difficulty of necking as in the case of tension and barreling as in the case of compression. So a material, when it is subjected to torsion, it is ductile, that means it undergoes some amount of plastic deformation when compared to that of tension test. So before going into the differences between the tension and torsion, we consider what is the type of failure for the case of a ductile material and what is the type of failure for the case of a brittle material. For the case of tension test, the stresses are the uniaxial tension test. That means the stress is applied along one direction. It is uniaxial. Whereas in the case of torsion, it is subjected to both tension and compression. So it is under biaxial state of stress. So now we see what is the state of stress at a point for a material which is subjected to torsion. So for the case of shaft, we have, this is the state of stress at a point where the material, it is subjected to torsion. Maximum shear stresses, these are the maximum shear stress, tau max, acting on planes perpendicular and parallel to the longitudinal axis. Perpendicular and parallel to the longitudinal axis. Shear stresses, maximum shear stress acting on planes parallel and perpendicular to the longitudinal axis. Maximum sigma 1, this is the tensile stress, principal stress, which acts perpendicular to a plane which makes an angle 45 degrees to the longitudinal and transverse axis. And sigma 3, which is equal in magnitude but of opposite sign, that is compression. It is another normal stress which acts perpendicular, which acts in a direction perpendicular to the plane which is at 45 degrees to the longitudinal and transverse axis. So this is the state of stress at a point, the component which is subjected to torsion. So the state of stress for the case of torsion is sigma 1 is equal to minus of sigma 3. For the case of a ductile material, it fails along the plane of maximum shear stress, which is generally perpendicular to the longitudinal axis. So this is the case of a ductile material which has failed along the plane of maximum shear stress, which is normal to the of longitudinal axis. A ductile material, and this is the case for a brittle material which has failed in torsion